Hey class, Adam Ward here. I want to talk to you about hardness and water softening, the process by which we remove hardness from our drinking water. So, first let's start with what do we mean when we talk about hardness? Hardness of water specifically is related to how many metallic polyvalent cations we have in our water. We call that hard water when we have a lot of these. And so, what we're specifically meaning here are these polyvalent, meaning charges of more than plus one, and cations, so positively charged. Now, primarily, our focus here is on calcium and magnesium, although some degree of hardness can be associated with iron, manganese, strontium, aluminum, and other trace metals. Now, the reason that we care about this is a fewfold. For one, hardness in water will lead to scaling, particularly any place that we're heating or boiling water, including our home and commercial water heaters and boilers that may be used for hot water or steam heat. Hard water makes soap and detergent less effective at grabbing and basically clinging to those dirt particles or small suspended solids in the water, so we'll end up using more, and often it feels like it's hard to rinse soap off in really hard water, so it leaves sort of a grimy feeling, not just on your skin, but also it leaves a scum in tubs, sinks, faucets, sort of a white calcium residue that tends to get left behind. And so, both because this is not optimal for our water users and at the end use, and it's dangerous to our infrastructure if we build up too much scaling, we want to remove that hardness before we send our water out for distribution. Now, one of the ways that hardness is expressed, and this is really common in textbooks, is hardness expressed as an equivalent weight. And so just a reminder, when we talk about equivalence, from a chemistry perspective, this is taking the mass per unit charge. And so I think the easiest way to do this is a quick example. The equivalent weight, EW, is equal to the molecular weight, MW, divided by Z, where that MW, again, is the molecular weight. So this would be sort of the standard that you would calculate from the periodic table, but you're dividing it by the valence charge. So as an example, let's think about carbonate as a polyatomic ion. So that's CO3 with a 2 minus charge. So its molecular weight we could calculate from the periodic table. 1 carbon with an atomic weight of 12, 3 oxygens about 13, so that's about 60 grams per mole. And you can see where those numbers are coming from. Its equivalent weight, however, would be its molecular weight divided by its valence charge. In this case, 60 grams per mole divided by 2 equivalents per mole. You can see that 2 because that's the charge on the grouping. And we end up with 30 grams per equivalent. And the idea here is to get everything in a per equivalent basis or a per charge unit basis, so that we can use both single ions that have a single charge, a double charge, a triple charge, and we can sort of use them interchangeably and not always have to go back to the balanced equation to deal with this. If you're thinking about concentrations, just as a quick aside, a concentration is a mass per unit volume, and our equivalent weight, we could do 1 over equivalent weight to get equivalents per mass. So we can actually get an equivalent concentration. So that might look like concentration multiplied by 1 over equivalent rate. And just to show you that with actual units at the bottom, we could have grams per cubic meter times equivalents per gram, and that would end us up with equivalents per cubic meter on the right-hand side. Now, with that in our back pocket, let's go ahead and talk about how we represent hardness, and there's a standard bar chart that we use to represent this. And so what we'll do is on the top bar, we'll list out all of our cations, and we're always going to do this in order of calcium, magnesium, sodium, and then potassium. And the way that we'll list these out is that the width of each bar is representative of the concentration in milliequivalents per liter. So we'll take that vertical line as 0 milliequivalents per liter. And whatever the concentration of calcium is, we make a bar of that width. Next to it, or sort of stacked on top of it horizontally, if you will, milligrams, milliequivalents per liter of magnesium, and so forth. So that's everything shown in blue. The text that you see written in red now is the bottom bar, and on the bottom bar we're going to write the anions that we've got in solution. And again, there's a particular order for this. First, we would write any of these OH groups or any bicarbonates, and that should be CO3 minus. We're always going to write those first. Now, most of the time, those are going to actually have concentrations of 0, so they won't exist. But if you have them, they belong on the left-hand side. Then we work our way to the right, including carbonate, sulfate, and chloride anions. And again, the width of those bars is representative of the concentration of each of those ions within the solution. Now, if we've got complete data, the sum of those concentrations of cations should be approximately equal to the sum of the anions. In reality, this is often not the case because you might have imperfect measurements or some other trace cations or anions in your system, but those should be awfully close to one another. And finally, if you're wondering about that box over on the left-hand side, the box on the left-hand side, you can see I've written carbon dioxide in there. This is the concentration of CO2 that's dissolved in your water, and you're going to also express that in terms of milliequivalents per liter. And as we go through the stoichiometry on subsequent slides, you'll see why that CO2 is important, and it comes to the left of, and so sort of by a English writing convention before the cations and anions that we deal with. Now, this chart is handy for us because it helps us think about which cations and anions are paired with one another. And there are a couple of terms that we use to try and describe this. So one is carbonate hardness, and that is describing for us the amount of hardness that is associated with our carbonate and bicarbonate anions. And so you can see graphically in orange where I've drawn that and labeled it carbonate hardness. Non-carbonate hardness is the rest of those polyvalent cations that are not associated with carbonate or bicarbonate. And so you can see that I've done this in green for you on this slide. It starts right where carbonate hardness ended, and that bar extends over to the right until we get to the right-hand side of that magnesium bar. So that's hardness we have to remove, but it's not associated with carbonate anions. Our total hardness is basically the width of that calcium bar plus the width of that magnesium bar, and those are added together. They're both in milliequivalents per liter, so we can add those right together. We call that our total hardness. Okay, so there are two possibilities here relating to alkalinity relative to total hardness. And so the first case is when our carbonate hardness is equal to our alkalinity. And just to remind us, alkalinity is the hardness associated just with that carbonate and bicarbonate group. I've labeled that here in pink for you. So, for example, let me just put some anions and cations into this top set of bar charts to show you what this case looks like. This is set up the same way as the previous slide. And so here I'm labeling some of the things that we might want to know about. So in this case, total hardness is in blue, and that's associated with the calcium and magnesium ions, right? So total hardness has to do with those 2+ and 3+ cations. That's where total hardness really comes from. In the dark red color where I've labeled it CH, that's the carbonate hardness. So that's how much of those calcium and magnesium ions goes with or is paired with or overlaps with carbonate and bicarbonate. The amount of hardness that is not carbonate is, of course, non-carbonate, labeled in green. And in this case, alkalinity is equal to carbonate hardness. So for this case, non-carbonate hardness is total minus carbonate, and alkalinity is equal to that carbonate hardness. But that doesn't have to be the way that our system works. There are cases in which the carbonate hardness might extend beyond those calcium and magnesium bars. And so now in the bottom set of bar chart, you can see that I've devised a system where, for whatever reason, we're much higher in carbonate than we are those calcium and magnesium ions. So in that case, alkalinity would be, again, the width of those bars associated with carbonate and bicarbonate, labeled in pink. Total hardness, again, is just the calcium plus magnesium. But here, carbonate hardness represents the same amount as total hardness. So all of those calcium and magnesiums are associated with bicarbonate. So that means there is no non-carbonate hardness in this case. So non-carbonate equals 0, and carbonate hardness equals total hardness. So the point of these is just to sort of get you comfortable with what are we talking about with hardness, and really driving home the idea that hardness is really about those calcium and magnesium ions. And the carbonate, non-carbonate part is what fraction of those bars or what width of those bars is associated with which anions. And in that bottom case, there is no width of calcium or magnesium that is associated with anything but carbonate. So nothing with sulfate or chloride, for example, so no non-carbonate hardness. Okay, so the process that we use to remove hardness is called lime soda ash softening, and I want to walk through the key chemical equations that describe how this works. And so we start with lime, and so lime is that CaOH2 molecule. Sometimes places will use what's called quicklime, which is calcium oxide, and as soon as you expose that calcium oxide to water, it immediately hydrates. It gets into this calcium hydroxide form and releases heat. And so either way, this calcium hydroxide, CaOH2, that's the lime that's ultimately going into our reactions. So what does that stuff have to do? Well, the first thing that we need to do is neutralize that CO2. So we had written that on the left side of our bar chart. It's a stronger acid than anything else that we have, and so it will react preferentially. So before we can deal with the constituents we want to remove, first we're going to have to deal with neutralizing any of the CO2 and the carbonic acid that it would create in our solution. So the key equation for you is here. CO2 plus our lime generates this calcium carbonate, and that little parentheses has an S in it, denoting a solid precipitate, and water. After we neutralize that CO2, we're going to deal with carbonate hardness. And so carbonate hardness, again, you can see that we've got our lime, our calcium hydroxide there, and the first term in that equation is a calcium that's associated with one of those carbonate anions. And this chemical reaction produces calcium carbonate, which will precipitate out as a solid, and two H2Os. And very similarly, if we've got magnesium that's associated with carbonate hardness, that lime also reacts there. We generate both a calcium carbonate precipitate and a magnesium hydroxide precipitate. So just to kind of reinforce this for you, by adding lime or quicklime, what we can do is we can precipitate out calcium carbonate and magnesium hydroxide out of the solution. And we're doing that as a result of the CO2 that was present and the calcium carbonate hardness and the magnesium carbonate hardness. So having dealt with carbonate hardness, unsurprisingly, the next thing we'll deal with is non-carbonate hardness. So here I'm writing down the equation that describes the removal of magnesium that would be associated with sulfate. And again, you can see we're using lime to form a precipitate. Now, it is also possible here that you would have a calcium sulfate, for example. You could have a calcium chloride or a magnesium chloride here. But this is the most common of the equations. And if you go back and look in your textbook, you'll see that there's a whole host of possible removals that have to happen at this step. And so again, lime in, solid precipitate out. Although you might notice that there's a slight problem with this one, as highlighted here in purple. By adding that lime, we're adding calcium to the very system we've been trying to get the calcium out of. And so while we did drop out the magnesium, we did so by adding extra calcium. So the final step here is we need to get rid of that calcium that we just put in. And so to do that, we add soda ash, which is this sodium carbonate, Na2CO3. And again, we'll form a calcium carbonate precipitate from that. So the final step, and why this is called lime soda ash softening, is after we're done with all of the lime that we've added, we then have to go through another step where we add soda ash to get rid of the lime byproducts that we didn't necessarily want there in the first place. What this actually looks like, one of the more common systems here is a two-stage lime soda ash softening. And I just want to walk you through sort of these steps. So you can imagine that as raw water comes in from the left, we're going to add lime to the system in a rapid mix tank. And one of the important things as we add this lime, lime is a basic, and it is going to up our pH, and we want to get pH up to around 11 to allow that magnesium hydroxide to also precipitate out. So we've added our lime, we get this chemical reaction happening, water flows into that first flocculator or clarifier, where settling is going to remove those precipitates, calcium carbonate and magnesium hydroxide. Water flows out of there and we go into a recarbonation step. And this step has, you can see that CO2 arrow coming in. So despite that we've tried to neutralize all of the CO2 up front, we're actually going to bubble in a small amount of CO2 again to lower the pH back down into the 9.5 to 10 range. Once we get our pH there, we next add soda ash, and again that's going through another rapid mix step, and that soda ash is going in to get out any of the remaining calcium ions that are dissolved. That water flows into the second flocculator clarifier, so the one that's sort of middle bottom of this image. And again, we let that calcium carbonate settle out. From there, we go into a second recarbonation step, and we bubble carbon dioxide back into the water, again creating carbonic acid and lowering the pH until we get it down to around 8.5. And the idea of lowering that pH is that it's going to prevent calcium carbonate from forming, which means it's not going to scale on our equipment, it's not going to start clogging up our pipes or change our mixing, and so we end up with what we would think of as stabilized water. The water softening process ends at that second recarbonation step where I've drawn that red dot, and everything after that, filtration or subsequent processes, are going to continue on their merry way through the system. But the two-stage process ends with that second recarbonation step. There are certainly alternatives. There's what's called a single-stage softening technique. There's a split technique where some of your water is allowed to bypass that first flocculator to try and control pH for the second without recarbonation. So there are several possibilities out there, but this one is one of the most common. If you are looking at this and saying to yourself, wait a minute, so we added lime to get rid of the CO2, and then we subsequently bubbled back in CO2. We intentionally added calcium carbonate Then we have another step to get rid of the calcium we just added. You're not missing something. It is as unintuitive as it sounds, but remember, all of these steps are about creating the exact conditions that we need for the chemical reaction that we want. So we're trying to control the physics and the chemistry of this problem to force the reactions to happen efficiently and in the directions that we want them in order to quickly stabilize this water and get it to a place that we can send it out to our customers. All right, so what you should be able to do after watching this lecture is, given concentrations, you ought to be able to draw your own bar chart representation of hardness, be able to understand alkalinity, total hardness, both carbonate and non-carbonate hardness, and you should be familiar with the key reactions that take place as we go through this lime and soda ash process. I hope this helps, and I'll see you all in class. Have a great one.